Okay, let me show you the contents of this video, which I will cover. First, I will introduce the topic, and then I will explain that what type of wavelet transform I should choose. I mean either CWT or DWT. Then I will explain the wavelet properties, which are very important, that will help us to select the appropriate wavelets. And then I will explain how to choose the wavelets for feature extraction, then wavelets for denoising, then wavelets for compression, and then wavelets for detection of the change point or the discontinuity detection. And in the last, I will explain the wavelets for a few other applications such as analysis of variance, watermarking, edge detection, ECG signal feature extractions, and OCR. So let's go ahead, but before going ahead, I strongly recommend you to watch following my two videos. The first one is about the introduction to the wavelet theory and its applications. So here you can find the CWT, DWT, filter banks realization, different wavelet types, and wavelet applications. So it's almost a complete package about the basics of the wavelet. So this video you can find on link which is given in the description. And then second video is about the continuous wavelet transform of 1D signals using Python and MATLAB. So here I have shown the both types of implementation using Python and MATLAB. And here you can see how to plot the scalograms, I mean the CWT coefficients, and I have taken one example of the discontinuity detection. So this is also a very good video to understand the basics of the wavelets. So this again you can find on the link which is given in the description. So now let's see how to choose a right wavelet. So this comes in everyone's mind whenever someone starts working on the wavelet first time, that which wavelet or which wavelet transform I should choose for my application. The answer of this problem is not always clear, but the few properties of the wavelets give actually the clear indication and help us to select the right wavelet and right wavelet transform. So now let's go to understand that which wavelet transform I should choose. Okay, so first we'll go for the basic properties of the transform, and then we do a comparative analysis, and on the basis of that we will derive our conclusion. So we have the two basic wavelet transform. One is the CWT, other is a DWT, I mean the continuous and the discrete form of transform. The CWT actually is redundant in nature, that's why known as the undecimated transform. It generates a huge amount of coefficients, while the DWT has actually the two form. One is non-decimated, which is as example known as MODWT, I mean the maximally overlapped discrete wavelet transform. This generates more coefficients, while the other form is the decimated form, whose example is the MRA, I mean the very popular multi-resolution analysis. So that generates the fewer coefficients. The CWT is not computationally efficient. As I said, it generates a huge amount of coefficients, while the DWT is more computationally efficient, and particularly the decimated one is more efficient because it generates a very less amount of wavelet coefficients. And the CWT is shift invariant. That is one good thing about CWT. But the decimated DWT, I mean such as MRA, is not shift invariant because we go for the DWT downsamplings, while the non-decimated form such as MODWT is a shift invariant because we do not go for downsampling of the coefficients. The CWT cannot be implemented with a filter bank, so that is a drawback. You cannot implement this in hardware. While the DWT, both the decimated and undecimated forms can be implemented with help of the filter banks, I mean the low pass and high pass filters. So this is one good thing. You can implement this DWT in hardware with help of the integrated circuits. The inverse operation ICWT, I mean the inverse transform, is not much accurate, and it's a very less stable numerical operation for continuous wavelet transform. While inverse DWT is more accurate reconstruction and it's a stable numerical operation with precision. So on the basis of these properties, we can conclude the following points. So if our application is to obtain the sparsest possible signal representation for such as compression, denoising, or let's say signal transmission, then DWT is a clear choice. So if our application requires an orthogonal transform, I mean the energy preservation, then DWT with the orthogonal wavelet filters is a obvious choice. Now, if our application requires a shift invariance transform, but we need the perfect reconstruction also, then the non-decimated form of DWT such as AMO DWT or dual tree complex transform is a choice. And if inverse transform is not required, then one can go for CWT. And if our primary goal is a detailed time frequency scale analysis or precise localization of some signal transient, then CWT is a good choice. We have few examples such as discontinuity detection, frequency break, etc. And for other applications which are important, of course, such as denoising, compression, feature extraction, studying some statistical properties of the wavelet coefficients, the DWT is definitely a good choice. So now let's see a few examples of the CWT. So here you can see that if you want to go for the time frequency analysis of some signal, then CWT is a obvious choice. So in this case, you can see that we have a hyperbolic chirp signal. It has a combination of the two signals, and here you can see that with the time the frequency is increasing. And this is the CWT plot, I mean the scaleogram of this chirp signal. So you can see these two highlighted lines of yellow color. So that is clear indication of increment in the frequency. So if you progress in the time, there is a increment in the frequency. Okay, so this is a very good representation of the signal property. So this is the similar operation which you generally do with a Fourier transform and its spectrum analysis. But here the advantage is that in Fourier transform we get only the frequency versus magnitude, but here we get the three axes, the frequency, magnitude, as well as the time. So that is the more advantage in the wavelet based time frequency analysis. And take another example for the discontinuity detection. So here the CWT coefficients for this signal shown. So you can see that these two discontinuities are well represented by these CWT coefficients at these time moments. And this is another example of frequency break. So here with the CWT coefficients, you can easily see that something happened at this time. I mean, there is a sudden change in the frequency. So here the frequency is less and here frequency is more. So that started at this time moment around 500 number of samples. And now let us see what is scaling function phi t. Actually, this is a very important aspects of the wavelet analysis, which I somehow missed in my previous video. So I'm taking it in this video. So it will also help you for the proper selection of the wavelets. So let's see what is the scaling function. If you remember in the previous video, I have included this, that a signal ST can be decomposed using the wavelet with the MRA, I mean the multi-resolution theory that was given by the Smollett and Mayer with help of the digital FIR filters as shown in this figure. So here you have one signal as, let's say it has 1,000 samples. So it passed through a high pass filter which is derived from actually the wavelet, and then output is downsampled by 2, and here we get the 500 DWT coefficients which are of nature high frequency. So these are known as the detail coefficients, generally represented by the CD, and when this signal is passed through the low pass filter and then downsampled by 2, we get the 500 coefficients which are of low frequency nature. So this is known as approximation coefficients represented by CA. So this is how we achieve the wavelet coefficients with help of the filters. But the question is that how these filters are obtained. So this HPF is obtained by the wavelet function psi t, while this LPF, I mean the low pass filter, is obtained by the scaling function phi t. So that is a combination of phi t and psi t. So few wavelets such as dB, Haar, Simlet, Wavelet, and bi-orthogonal wavelets, they have their corresponding scaling functions. Not all wavelets has this phi t psi t combination. Okay, so that we will see in the properties part later in this video. So this is quite important aspects of the wavelet. So as an example, I have taken the Simlet 4. So here I have shown the scaling function of this Simlet 4. So this is the phi t psi t combination, you can see. So this is Simlet 4 wavelet and this is its scaling function. And here you can see all the 4 filters. These 2 are for decomposition. So these LPF, one for decomposition and one for reconstruction. So these LPFs are derived from this scaling function, while the HPF, one for decomposition and one for reconstruction, these 2 filters are derived from the wavelet function. So this is the role of the scaling function. Now let's go through the wavelet properties. So the first one, which is very important, that is the vanishing moment. So let's see what is this vanishing moment. The vanishing moment is a criterion about how a function ft decays towards the infinity. So we can estimate the rate of the decay by the following integration. So if we can do this operation and we achieve the 0, it means this k indicates the rate of decay. Okay, so here we can take one example. Suppose my function ft is sine t upon t square. So I can do the same operation for this function. So integrating from minus infinity to plus infinity, t power k ft, or I mean the sine t upon t square. I mean sine t upon t square dt. So if I choose, let's say, k equal to 0, so my remaining function will be the same, that is sine t upon t square dt. And if I do this integration, of course, I will get 0. And if I choose k equal to 1, then this integration will be from minus infinity to plus infinity. And this is t sine t upon t square. So this t to t cancels, only we get sine t upon t. So this equals to pi. So I mean this integration converges, and if I choose k equal to 2, then this will be the integration from minus infinity to plus infinity, t square sine t upon t square. So this is the integration of the sine t, so that will not converge. So here we can see that for k equal to 0, 1, for these 2 values, this integration converges. So we'll say that number of vanishing moments for this function will be the 2. The same you can apply for a wavelet function psi t also. So a wavelet function will have the n number of vanishing moments if this satisfies this integration, where k is equal to 0, let's say 1, 2, 3 and less than n. Okay, the same thing which I have shown you here. So this is a very important property which actually shows that how a wavelet function or how fast a wavelet function decays in time. So on the basis of that, we have the few observations. So the Fourier transform of both phi t and psi t, I mean the scaling function and the wavelet function, they have their first n minus derivatives which are 0 at omega equal to 0. And the Fourier transform h phi, which is the Fourier transform of the wavelet filter, which is obtained by the scaling function phi t. So of course this is LPF. So this Fourier transform and its first n minus 1 derivatives will have the 0 value at omega equal to pi. And from this information or the number of vanishing moments, we can construct the polynomial of the degree k like this. And a wavelet with n vanishing moments is orthogonal to the polynomial of degree n minus 1. So here we have one important observation, that number of vanishing moments and the oscillations of the wavelet have the loose relationship. So as the number of vanishing moment grows, the wavelet oscillations also grows. So this you can see in this figure. So we have the 3 wavelets for comparison. So it has number of vanishing moment 2, it has number of vanishing moments 4, it has vanishing number 8. So you can see the as n is increasing, I mean the number of vanishing moments is increasing, the oscillation of the wavelet is also increasing. So it has a less oscillation. Then you can see that dB8 has a highest oscillations. So actually the names of many wavelets are derived from the number of vanishing moments. So for example, the name of Denoising family and the Symmetry family is derived from their corresponding vanishing moments. So for example, if you take the dB6 wavelet, it means it has the 6 number of vanishing moments, and for Sim3 it has the 3 vanishing moments. For coif n, this is slightly different. For coif n, the number of vanishing moments are actually 2n. So for a coif 3, the number of vanishing moments will be 6. Similarly, we have the nomenclature for bi-orthogonal wavelet, but here we get the 2 numbers instead of 1, such as bi or 3.5. Actually 2 numbers because these are 2 different vanishing moments. Bi-orthogonal wavelets are different than normal wavelets. They have different wavelet functions for analysis and reconstructions. Okay, so for example, in case of bi 3.5, the 3 is actually representing the vanishing moment for the wavelet which is used for synthesis, I mean the reconstruction, and the 5 is representing the number of vanishing moments for the wavelet which is actually used in analysis, I mean the decomposition. So that is how we get the names of different wavelets from their number of vanishing moments. And now the second important one is the support size. So actually the size of the support indicates the length of the FIR filter, I mean the number of samples in their impulse response. So if an FIR filter has n number of samples in their impulse response Hn, then support width for that wavelet is known as n minus 1. For the wavelets Har, dB and Simlet, the number of vanishing moment of course is n, as clear by their name, and their corresponding filter length is 2n, and the support width is known as a 2n minus 1. And for Wavelet, the number of vanishing moment is 2n and the length of the filter is obtained by 6n. So here is one example of the Simlet 4. So Simlet 4 means the number of vanishing moments are 4, and here you can see that the support width is 2n, I mean the length of the filter is 2n. So that means 4 into 2 means 8. So here you can see that there are total 8 samples in all these filters from 0 to 7. Okay, so this is how the length of the filter is related with the number of vanishing moments. So more vanishing moments is clearly meaning that the length of the filter will be more. And the third one is the regularity. That is another very important one. So the regularity is related to how many continuous derivatives a function has. So intuitively, the regularity can be considered as a measure of the smoothness of the wavelet function. So a wavelet with the more vanishing moments will be more regular. So this we can see with this example. So we have taken 2 examples. One is of dB2 and dB10. So this is the scaling function of dB2 and this is a wavelet function of dB2, and here you can see for dB10. So now see which one is more regular. Of course, this is more smoother. I mean the dB10 scaling function and wavelet function are more smoother than the scaling functions and wavelet function of the dB2. So you can compare their corresponding vanishing moment. So for dB2 the vanishing moment is 2 and for dB10 vanishing moment is 10. So more vanishing moments means more smoother and more regular wavelet. And now let's see the symmetry, another very important one. The symmetry actually concerns whether the wavelet filter characteristics have the linear phase or not. So a dB, I mean the Dobshi is not a symmetric wavelet, it's an asymmetric wavelet. So it exhibits the non-linear phase angle, while the Simlet, Wavelet They are also not symmetric, but they are near symmetric. So we get almost a linear phase from them. And bi-orthogonal is symmetric. So we get the linear phase angle from the bi-orthogonal wavelet family. So this you can understand with this example. So we have taken the Darvishi-4 scaling function, and this is the blue one is showing its phase angle in the frequency domain. So you can see that this is nonlinear. So as I said that dB is a symmetric wavelet, so it gives the nonlinear phase. And now see the bi-orthogonal 3.5 scaling function, which is used for reconstruction. So you can see in time domain also that this is not symmetric while this is quite symmetric. And also in frequency domain you can see that we are getting a perfect linear phase for bi-orthogonal wavelets. So that is important property, and that will be used later in the selection for appropriate wavelet for different applications. So that I will explain in the later slides. And the next one is orthogonality. That is also very important one. So if wavelet is orthogonal, the wavelet transform preserves the energy. I mean, you can get the perfect reconstruction. So you don't lose actually the information during the analysis and synthesis part. So the strict orthogonality is actually the beneficial to achieve the accurate reconstruction of the signal from its coefficients. So the scaling function phi t and wavelet function psi t are orthogonal. So we have this family Haar, dB, Sim, Coef, Mayer, De Mayer, Bettelheim. These all are orthogonal wavelets, while Bayer and reverse Bayer, they are bi-orthogonal, while the other remaining wavelets are not orthogonal. So we have to choose carefully on the basis of this orthogonality. And now let's see the properties of the wavelet summary. So this is a table which actually representing the summary of all the properties, and few other are also added. So here I have taken all major wavelets, and in this column you can see all the properties. So the first one is the infinite regularity, and here you can see that wavelets which support this are highlighted by this green color. So infinite regularity, the wavelets which can be differentiated infinitely are supported by the Morlet, Mexican hat, Mayer, etc. And the arbitrary regularity supported by the Bettelheim, dB, Simlet, Coeflet, and by orthogonal wavelet. And now these are the wavelets with the compact support. These are orthogonal with the compact support, and this is bi-orthogonal with the compact support. And these are the wavelets which show the symmetry property, except this group dB, Simlet, and Coeflet. As I already explained that dB is asymmetric, while the Coeflet and Simlet are near symmetric. Okay. The existence of a scaling function. So these wavelets have their corresponding scaling functions. So these are the other properties such as these wavelets supports the orthogonal analysis, and these wavelets also support the bi-orthogonal analysis. Exact reconstruction, the inverse transform is supported by these wavelets, except these. They support actually the near exact reconstructions, not perfect one, and the FIR filter support. So these group of wavelet actually support the realization using the digital FIR filters, and these wavelets are useful in CWT analysis, while these wavelets are useful in DWT analysis. The fast algorithm is available to compute the wavelet coefficients for this group, and this is a group which is widely used for wavelet applications. So, and also it is supported by the FIR filters. So these type of wavelets are implemented largely in form of the hardware with integrated circuits. And in the last, the explicit expression, it means these wavelets have actually the exact mathematical representation, while others do not have. And this is another table which classify the different types of wavelets. So the two major categories I have shown here, the one with the filters and one without the filters. So one with the filters further divided into two with compact support, with non-compact support, and then further divided into orthogonal and bi-orthogonal. So the DB, HAR, SIM, COIF, these are the wavelets which are orthogonal with the compact support and with the wavelet filters. And this is the group Mayer, DeMayer, Bateley-Mayer. They are orthogonal, but they do not show the compact support, but can be realized with the filters. And here in this group, we have the two divisions, real and complex wavelets. So this group, Gaussian, Mexican, hat, Morlet, they are real wavelet functions, while these wavelets are the members of the complex wavelet functions. And now let us see how to choose the wavelets for different applications on the basis of these properties we have just understood. So for this purpose, I'm taking the first example, that is wavelets for feature extraction. So if we want to find the closely spaced features, then we should choose the wavelets with a smaller support, such as HAR, DB2, SIM2. You should not go for the higher vanishing moments wavelets such as DB10 or BIR 6.8 or something, because this support of the wavelet is small. For example, the HAR has only the 2 samples in its impulse response of the wavelet filter. So if this support is small, then it is able to actually distinguish the closely spaced features. So wavelets with larger support will create the difficulty in detecting the closely spaced features, and wavelet with large support will generate the coefficients from which it will be very difficult to distinguish the individual features. So this we can understand with this example. So here I have taken one signal S, which has these closely spaced samples, I mean the near to each other. So I have decomposed this with the wavelet HAR, of course that is the less support. And here if you see these wavelet coefficients, detailed coefficients at level 1, you can see that these features which are closely spaced are well distinguished or well represented by these wavelet coefficients at level 1. So this is one good example. And same signal you can see that what happens if it is decomposed with the wavelets with higher support, I mean the DB6. So DB6 means there will be the 12 samples in the filters, corresponding filters. So here you can see, if you visualize this D1 and compare with the previous one, so here you can see that these features are not well represented by these coefficients. Okay, so this is how you can select a low support wavelet, I mean the wavelet which has the less number of samples in its filters for such closely spaced features. Okay, so that is useful for both signals and images. In case of images, there can be a fine edge patterns where there is a close placement of edges. So you should go for lower support wavelets. And now other one is the wavelets for denoising. So this is just example, just for demonstration, a noisy and denoised version. So an orthogonal wavelet such as the Simlet and Dobeschi wavelet, it's a good choice for denoising signal. The bi-orthogonal wavelet is also very good for image processing, because the bi-orthogonal wavelet filters have the linear phase, and that linear phase is very critical for image construction, because this linear phase will not introduce any visual distortion in the images. So the Simlet 4 is a good choice for signals denoising, I mean for one dimensional, and for images the BIR 4.4 is a good choice. Okay, and now let's see wavelets for the compression. So we should consider the bi-orthogonal wavelets, particularly the BIR 4.4 and reverse BIR 3.9 for compression, because they are symmetric and they have the linear phase. So the wavelets actually with higher vanishing moment should also be selected, because such wavelets produce the fewer significant coefficients during the decomposition. So therefore the majority of the coefficients can be neglected while keeping these the lesser significant coefficients. So that will achieve the image compression. Also, the higher vanishing moments causes the more regular wavelets, I mean the more smoother wavelet. Therefore, the smooth reconstruction of the image will be achieved. So here in this example, you can see the difference. This is my original image, and this is the outcome of compression with a HAR, and this is outcome of compression with a Bayer 4.4. So here in this image, you can see that this discrete effect, I mean pixelite effect, because of this HAR. And if you choose the Bayer 4.4, you get more smoother reconstruction because of this more regular wavelet. So in the compression, we should choose the wavelets which are symmetric, which have the linear phase, and which have the higher vanishing moments. Okay. And now let's see the wavelets for the change point or discontinuity detection. So to detect the instances where a signal has changed its value, the wavelet with the higher vanishing moments, I mean the more regular wavelet, should be selected. So this we can understand with this example. So here I have my signal which has actually the change in its value at this moment. So initially it is flat, and then its value increases. So let me show you that how you can detect this time instant. So here you can see the two figures. In first, I have shown the detail coefficients at label 1, which is obtained by decomposition using dB1, I mean the HAR. And the second one is showing the detail coefficients at label 1 using the dB3. So there is a clear difference in these two figures, that this second one is giving the better representation of this change in the value at this time moment, while this is not a good representation. So this gives the idea that the higher vanishing moment wavelets are more suitable for obtaining such change point detection in the signals. And next, you can take another example of the frequency break. So here I have a signal which changes its frequency suddenly at the 500. So these are the detail coefficients at label 1, which are obtained by the HAR decomposition. And now compare this with this figure. Here these are the detail coefficients at label 1, which are obtained by the dB10. So you can see that this is a very good representation of to know that something happened at the 500 in comparison with this one. So obviously it is showing that you should choose the wavelets with the more vanishing moments for such discontinuity detection. And now let's see the other applications. One is analysis of variance. So if our goal is to conduct actually an analysis of variance, I mean you want to see the change in a trend of a signal, then maximum overlap discrete wavelet transform, I mean the MODWT, is suitable. So the MODWT actually conserves energy in the analysis by use of some orthogonal wavelets such as TB, Simlet, etc. And the MODWT partitions the variance across the scales. So therefore, it is very much suitable for analyzing some financial data series or some other series for change point detection. So here you can see in this example that this is the graph of the US GDP from 1947 to 2008. Here, if you look this graph, you will not have any idea that what happened in 1982, after 1982. So if you go through the wavelet decomposition, these are the wavelet coefficients at label 1, detail coefficients. So you can see this, that there is a change in the trend after 1982. So this is how you can use this MODWT to analyze the variance. And let's see other applications such as image watermarking. So for image watermarking, wavelets with a higher vanishing moments, I mean the more regular, and symmetric wavelets, I mean having the linear phase, should be selected, such as the Bayer 6.8. And for edge detection, this is of course similar to the feature detection, which I have already covered in the first example. So here the wavelets with a smaller support, I mean the less vanishing moments, should be selected, such as HAR, dB2, Bayer 1.1, etc. For ECG signal, Simlet 4 is widely used for this purpose. There is a one good thing about the Simlet 4 is that its shape is very much matching with the shape of the ECG signal, so it generates a large coefficients. So it's a good choice. And for feature extraction of the OCR, Again, the wavelets with a higher vanishing moment should be selected, such as DV10 or equivalent. So we have now covered various applications and their selection for appropriate wavelet. So I hope you have understood these things, these wavelet properties, and I hope that whenever next time you will go for the selection of the wavelet, you will have these things in your mind for the proper selection of the wavelets for your applications. So that's it for this video. I hope you have enjoyed it. So thank you very much, all of you, for watching this video. I request you to please like it, share it. Goodbye.